Hi, today we're going to talk about formal charge. What is it and why do we care? So the first thing you should know about formal charge is it is a theoretical value. And in some ways it has absolutely no physical meaning. But it does help us to predict a lot of things about molecular structure. So basically formal charge is the charge that an atom in a molecule would have if all atoms had the same electronegativity, which doesn't make a lot of sense right now. So let's look at how to calculate formal charge and look at an example. And then I'm going to circle around and talk about what this definition actually means. So officially, we calculate formal charge by calculating the number of valence electrons in a free atom. In other words, if you just had one atom not bonded to anything, how many valence electrons would it have? And from that, we're going to subtract the number of valence electrons in the atom that you do have, which is bonded to one or more other atoms. Let's clarify that second part just a bit. The number of valence electrons in a bonded atom are going to be equal to the number of unshared electrons, and then half of the shared or bonding electrons. Now, half of the shared or bonding electrons turns out to be the same number as the number of bonds that you have, and often it's easiest to just do it that way. Now, when you're calculating formal charges, you have to calculate the formal charge for each atom in a molecule. So now let's look at an example, and we're going to start with a fairly easy molecule, carbon monoxide. So I've gone ahead and drawn the electron dot structure here. Note that you will not often be given the structure. You will usually have to draw it yourself, and in fact, we're going to do that later in this video. Let's calculate the formal charges, and remember, we have to do it for every atom, so we're going to have to do it for carbon, and we're going to have to do it for oxygen. We're going to start with oxygen. The first thing we have to ask ourselves is how many valence electrons does oxygen normally have? And so that number is 6. And from 6, we're going to subtract what's in parentheses here, the number of unshared electrons around an atom. These are the unshared electrons here. We have 2 of them, so we put 2 here. And then the other thing is that we have to put 1/2 of the shared electrons, which is equal to the number of bonds. So you can see we have a triple bond here, and that would be 6 electrons, but we're only taking half of them. So we have 3 for this value here, which also happens to be the number of bonds because it's a triple bond. So the parentheses 2 plus 3 is equal to 5. 6 minus 5 is plus 1. Now let's calculate the formal charge on carbon. Carbon generally has 4 electrons in its valence shell. And now if we look at the number of electrons it has in this molecule, it's got 2 unshared electrons again, and then half of our shared or bonding electrons, so that's going to be 3. So we have 5 in the parentheses again. 4 minus 5 is going to be minus 1. So in this molecule, we have plus 1 charge on oxygen and a minus 1 charge on carbon. So I've had a lot of students with questions about formal charge, and one of the questions I'm asked is, wait a second, we set up our electron dot structure so that everything has 8 electrons, and here we are calculating a different number of electrons for each atom in the molecule, but they all should have 8. What is this thing? So I'm going to give you an analogy. So we have these 2 aliens, alien A and alien B, and we're going to look at alien A on the left here in particular. So alien A and alien B are married, and alien A wants to buy a car. So when they go in to apply for a loan, the loan officer asks, how much do you have in savings? We want to know. Well, alien A has $10,000 in a single owner bank account. So that is alien A's personal money. Alien B, the spouse, has $8,000 in a sole owner bank account. And then they have a joint account with $16,000 in it. When the loan officer goes to look at how much money alien A can access, because alien A is married, the loan officer thinks, okay, they have access to $10,000 of their own plus $16,000 of joint money. So that's $26,000. Now let's look at what would happen if alien A and alien B got a divorce. So what they're going to do is they're going to take their joint assets, $16,000, and they're going to divide it in half. So we've got each getting $8,000 from that pot. And now when alien A goes to apply for a car loan, they have $18,000. Okay, so same amount of money, but we're looking at it completely differently. And this is the way that we can think about the two different ways of allocating electrons. One is looking at those shared electrons as a pool that both atoms can draw from. And the other way is to say, what if we split these up and they each got exactly half of the electrons? That's formal charge. You might say, some people, when they get divorced, don't split things 50-50. And this is 100% absolutely true. I know it from experience. In reality, with atoms, that would also be the case because some atoms are more electronegative than others. They're going to hold on to more shared electrons. And this is why formal charge is a theoretical value, because they probably wouldn't share the electrons evenly. But this is what we're doing. We're doing it as a theoretical value of, if we split the shared electrons exactly halfway, what would their electron assets be? So why would we even calculate formal charge? The answer is that if you're trying to draw a structure for a molecule and there are multiple possibilities for the structure, you can use formal charges to determine which of them are more likely to be observed in nature. And the structures we observe tend to follow very specific rules. First of all, molecules tend to minimize non-zero formal charges. In other words, it's preferable if everything is zero. But if you can't have everything zero and still follow other rules like octet rules, you're going to have the smallest possible numbers. So if you can't have all zero, you might have, for example, a -1 and a +1. That would be preferred over a -2 and a +2, or two -1s and two +1s. When you have to have non-zero numbers, if you're going to have negative formal charges, those will go on more electronegative atoms, whereas the positive formal charges will go on the less electronegative atoms. Let's look at carbon monoxide again. There are ways to make this so that there is a formal charge of 0 on both molecules, but you can't do that and meet the octet rule. And so we have to have this structure. And so this is not a very good structure because, in fact, it has no 0 formal charges. It has the negative formal charge on the less electronegative atom and the positive formal charge on the more electronegative atom. And that is why carbon monoxide is so unstable and so reactive. Now, one thing I should add that is always true is that the formal charges on the atoms in a molecule add up to the charge on the molecule. So in this case, we have -1 plus +1 equals 0. And we have a neutral molecule. If you had an ion, the formal charges would add up to the charge on the ion. So let's talk about a different carbon oxide molecule, CO2. And we're going to actually draw a couple of different structures for the molecule. And we're going to use formal charge to figure out which of these is the structure that we're most likely to see in nature. So let's go through and let's do this the way we were doing it in our electron dot structure video. Let's find the total number of valence electrons. So carbon has 4. We have 2 oxygens with 6 each, so that's going to be 12. And that means we have 16 valence electrons. Now let's move on to determining the number of electrons we need to complete the valence shell. Carbon needs 8. Each of our 2 oxygens needs 8, which means 16 from the oxygens, so that's 24. And then determine the number of shared electrons. So that's going to be 24 minus 16. So that will be 8. And that means that our number of bonds will be 4. So we have 4 bonds. Now we're going to draw the structure. Let's write the symbols for the atoms and put in the bonds. So carbon, oxygen, oxygen. And now we have to put in our 4 bonds. So 1, 2. There are 2 more bonds that we have to put in. How could we distribute them? We could distribute it this way with 2 bonds between the carbon and each oxygen, or we could distribute it this way with a triple bond between carbon and 1 oxygen and a single bond between carbon and the other oxygen. So for both of these, let's distribute the unshared electrons. Now, we started with 16 electrons and we've used 8 of them, so we have 8 left. In the top structure, Each of the oxygens has 4 shared electrons, which means they each need 4 more unshared electrons, and that takes care of our 8. In the bottom structure, the oxygen on the left has 2 shared electrons, so it needs 6. And the oxygen on the right has 6 shared electrons, so it needs 2. So both of these have octets on all of the atoms. They use the correct number of electrons, but these are not structurally similar. So again, the formula for formal charge has us subtracting the number of valence electrons in the free atom from the number of electrons around the atom in the molecule. So let's first look at this structure on the left. Start with the oxygen on the left. As you can see, it has 6 unshared electrons and it has 1 bond, so that's a total of 7. So we have 6 minus 6 plus 1, which is 7, equals minus 1. How about the other oxygen in this molecule? We've got 2 unshared electrons and we have 3 is the half of the shared electrons, right? 3 bonds. So 6 minus 2 plus 3 equals 6 minus 5 is plus 1. And then we have carbon, which just has 4 bonds. 4 is its normal number of valence electrons, so 4 minus 4 is 0. If we look at the structure on the right, look at the first oxygen, we see it has 4 unshared electrons and it has 2 bonds. 6 minus 4 plus 2 is 0, and I have to point out that the oxygen on the right has the exact same electron configuration, so they both are going to have a formal charge of 0, and the carbon, again, is going to have 4 minus 4 equals 0 for its formal charge. So if you look at our rules over here on the left, you'll notice that non-zero formal charges are supposed to be minimized. In this structure right here, we have a minus 1, a plus 1, and a 0. So we have 1 0 formal charge and 2 non-zero ones. And in this structure on the right, everything is 0. So that's going to be what we expect to see in nature. Now you might ask yourself, how do we know what these look like in nature? Can we actually see bonds? And while we can't necessarily, what we can see is the distance between the 2 nuclei. And it turns out that the more bonds you have between nuclei, the closer they are. So if you have this structure right here, you should see 2 different bond lengths, one longer and one shorter. And if you see this one over here, you should see 2 equal bond lengths. And that is, in fact, what we see in carbon dioxide. So now we're going to look at a molecule which I hope no one ever makes again, phosgene. Phosgene is actually a chemical weapon, has similar properties to mustard gas, and it was actually used in World War I. So the formula for phosgene is COCl2, and we're going to draw this structure. So let's pop into our normal steps. Let's find the total number of valence electrons. Carbon has 4, oxygen has 6, chlorine, we've got 2 of those, and each of those has 7, so that gives us 14. And so if you add those all up, you get 24. Now let's figure out how many electrons we need to complete our valence shells. Carbon needs 8. Oxygen needs 8. Each of our chlorines needs 8, so that's 16 from the chlorines. And so we need 32. So our number of shared electrons is 32 minus 24. That's going to be 8. And then there's the number of bonds, which is going to be 4. So now we're on to the drawing phase. So we're going to write the symbols for the atoms and put in bonds. Now you'll remember in the last video when we were talking about which atom is going to be in the center, it's always going to be the least electronegative atom. And in this case, that is carbon. So let's throw carbon in the center and let's throw our other atoms around it. And now we're going to put in bonds. We're going to put in 1, 2, 3, but we need 4. So we have to put a double bond in somewhere. So we have a choice. We can put a double bond between oxygen and carbon, or we can put in a double bond between carbon and chlorine. Which way is best? Well, let's put the double bond to oxygen, and let's also put the double bond to chlorine. Let's finish both of these structures, and then we will evaluate formal charge. So now let's distribute unshared electrons for each of these structures. We started with 24 electrons. We've used 8. That leaves us with 16. So the oxygen in this structure has 4 shared electrons. It needs 4 more. The chlorines each have 2 shared electrons, so they each need 6. And so 6, 6, and 4 is 16. We've used all of our electrons. In the bottom structure, the oxygen has 2 shared electrons, so it needs 6. This top chlorine has 4 shared electrons, so it needs 4. And the chlorine off to the right has 2 shared electrons, so it's going to need 6. 6, 4, and 6 gives us 16, so we've used all of our electrons. So here are the 2 structures. So let's start with our double bonded chlorine. This oxygen wants 6 electrons, and it has 2, 4, 6 unshared electrons and 1 bond, so that's going to be 6 minus 7. That gives us a formal charge of -1. We have each chlorine wanting 7. This one right here has 2 shared electrons and 4 unshared electrons, so that's 6, and that gives us a +1 charge. This one over here has 6 unshared electrons and 1 of the shared electrons, so that's 7, so this has a formal charge of 0. And then the carbon has 4 shared electrons, so that gives it a 0. Now let's look at the double bonded oxygen. This chlorine is the same as it was in the previous molecule. That hasn't changed, so that's still going to be 0. Our carbon is exactly the same, so that is also 0. Our oxygen wants 6, has 4 unshared and 2 shared electrons, so that's 0. And then our chlorine wants 7, has 6 unshared and 1 shared electron, so that's also 0. Now, again, remember the rule that the charges have to add up to the formal charge on the molecule. This one right here, all zeros, obviously adds to 0. This one down here, the +1 and the -1 will cancel each other out. So again, the total charges are 0. And that's a good way to double check that you've done your math right. If you haven't done your math right, it will not equal the charge on the molecule. So again, we're using this one where the non-zero formal charges are minimized. So which of these structures is the correct one? Again, we're going to look at this rule right here that minimizes non-zero formal charges. We do have a structure that has all 0 formal charges, and it is this one with the double bonded oxygen. So formal charges are going to help us a lot in distinguishing which possible structures are what we're going to see in nature. And so while they don't really have a physical meaning, they really help us with understanding why electrons end up where they end up. I hope this was helpful, and I look forward to seeing you again soon.